Well, good day, everyone, and welcome to this EDS technical lecture. And today we have with us Professor Leon from University of California, Berkeley. And it is our privilege and matter of honor for the EDS Delhi chapter to host this particular technical lecture jointly with Deen Dayal Upadhyay College, University of Delhi, under the aegis of the Department of Biotechnology's Star College program. The EDS Delhi chapter was established in 2007, and it is in 15 years of its existence. And we have organized several technical lectures, talks by Nobel laureates, EDS celebrated members, fellows of various science and engineering academies, including IEEE. And this is the 75th year of the invention of transistor. So as an EDS society, we decided that we are going to celebrate the year 2022 and 2023 to celebrate the 75th anniversary of the transistor. And it's a matter of pride for all of us that Professor Leon has kindly agreed to deliver the first technical lecture in this series. And the title of his talk is Memristor, Workhorse for Post-Morse and Non-Von Neumann Competition. He is a well-known figure in IEEE Electron Device Society and being the 2019 IEEE EDS celebrated member. But as a customary, I'll briefly discuss and enlighten all the attendees who are listening to this particular talk about his significant achievements of more than 6 decades. He's a life fellow of IEEE, and he became an assistant professor of electrical engineering at Purdue University in 1964 and was promoted to associate professor in 1967. He joined the UC Berkeley faculty in 1970 and is widely known for his invention of the Memristor. When not immersed in science, he relaxes by searching for a Wagner's Leitmotifs, musing over Kandinsky's chaos and contemplating Wittgenstein's inner thoughts. His research has been recognized through 17 honorary doctorates from major universities in Europe and Japan and holds 7 US patents. He was elected as the Confederate Julius Rohr in 2000. He is the first recipient of the 2005 Gustav Kirchhoff Award, the highest IEEE technical field award for outstanding contributions to the fundamentals of any aspect of electronic circuits and systems that has a long-term significance or impact. He was also awarded the prestigious IEEE Neural Networks Pioneer Award in year 2000 for his contribution in neural networks. He was elected a fellow of the IEEE in 1974 and has received many international prizes, including the IEEE Browder J. Thompson Memorial Prize in 1972, the IEEE W.R.J. Baker Prize in 1978, the Frederick Emmons Award in 1974, the M.E. Van Valkenburg Award in 1995, and again in 1998. He was a foreign member of the European Academy of Sciences in 1997 and the Hungarian Academy of Sciences in 2007. He was conferred the 2019 IEEE EDS Celebrated Member Prize, the highest recognition of the IEEE Electron Device Society, and the 2020 Julius Springer Prize in Applied Physics. With these words, I now invite Professor Leon to kindly share his screen and enlighten all of us.
Good morning, ladies and gentlemen. What I'd like to speak about today is a new workhorse for post-Moore's law era. Let me start by showing you this famous slide, starting with the picture of Jack Kirby, who is the Nobel Prize winner. By the way, we are going to meet many Nobel Prize winners today in my talk, and many of them are associated with the Memristor. He will be the first one who invented the way to make integrated circuits that can pack millions and now even billions of transistors on a chip. The Moore's law essentially says in this semi-log plot that the number of transistors that you can pack in an integrated circuit doubles every 2 years. And this prediction has been correct until very recently, namely on August 28, 2018. On that date, just a minute, I have to go back to on that date, IEEE Spectrum had a major short announcement, but important one is an event announcement that the global foundry, which is a few world famous silicon foundry that make the densest the devices. So this global foundry announces that it stopped producing 7 nanometer chip after spending billions of dollars installing extreme ultraviolet lithography, which is the current state of the art. After installing such an expensive equipment, it finds itself doesn't have enough customer for it. So it's not that you cannot make smaller one, it's just that it becomes too expensive to produce them. That's the reason. So the law in that sense is no longer valid. And that is indicated on the far right, August 28, that is where the Ohm's law era ends. And now we call this, that beginning of that date, the end of the Moore's law era and the beginning of this the post-Moore's law era, post-Moore era. So now we need to have a new device that will replace, that not exactly replace, but will take over the function of the Moore's law, still using the old CMOS technology, but with extra new devices to bolster its performance. That device is called the Memristor. And this is the new workhorse, the subject of my talk today. The quick introduction for those of you who may not understand what this problem is. All of the computers, from the supercomputer that are still in use today, that is used in deep learning, that was used to beat the chess contest or Go game. All those computers are based on von Neumann architecture. That architecture has hit a memory world in the sense that they are all based on separating the computation part, which is called processing unit on the left, and the memory unit on a separate location. So even with starting with the simplest task, adding 2 numbers, if you were to add 2 numbers, presently from the supercomputer or from your iPhone, you will have to find these 2 numbers that you want to add on the memory unit on a location on your chip, on your iPhone perhaps, or on your watch, and then bring that to a different location on the chip called the processing unit. Make the calculation, which typically is extremely fast, and then return it to be stored in the memory unit. That is where the time takes place. The shuttling time is too much to pay for. So that is called the curse of the memory world, in the sense that there is a gross mismatch in processing and shuttling time. Energy for memory access growing exponentially from the cache to off-chip DRAM, for example. Let us just look at the extreme case. The deep learning network that was used to defeat the AlphaGo 0. That was the game Go that what that was used to defeat the world champion in the game of Go. What does it take to do that? Well, it takes 64 GPU, 19 CPU, 4 TPU, 40 days of training, 29 million games of self-play, and 3.1 million mini batches of 2,048 positions, each of parameter updates. That's what it takes to win the game of Go, to beat the world champion. And the amount of energy, let alone the months, the amount of time needed to win this champion, to beat the champion, world champion, is just enormous. That's an extreme, of course, but just to show you where the problem was. Most time and energy are wasted in shuttling data. Most computing tasks in AI applications consist of machine learning operations, such as object, image, and speech recognition, where most energy and time are consumed in data movement rather than computation. In-memory computing via Memristor is the current method that would overcome such difficulty. On the left is the current for Neumann architecture, where I just show you that the arithmetic unit on the middle top and the memory location in the lower part, creating this memory wall problem. On the right is using now the Memristor-based logic in memory. In other words, the memory is now mixed together with the processing. And the way to do that is you need some device, new devices that is small enough to be able to incorporate them together, mix them together. And that device is the Memristor. And so this is called in-memory computing. That's what is being done at least at present. What can we do in post-Moore era? Well, the first thing, obvious thing now, is to dump the von Neumann architecture. That's obvious, and it's being done. That doesn't mean to throw away what we have. We still keep them. After spending billions and years of money, we are going to keep them, but we're just going to bring in new devices to bolster its performance, to avoid having to go from one place to the other place, but put them in the same place, for example. So we do what is now called in-memory computing. Number 3, we do something even better. We're going to do neuromorphic brain-like computing, which is what we are going to really talk about today. We are going to be able to do, or trying to do, computing at the level that beginning to imitate our brain. And finally, to be able to do that, the current device and technology that would enabling such a technology is the Memristor. So what is a Memristor? For those of you in the audience that may not know what it is, you will hear this device many more times today and in the future as well. The symbol of Memristor is on the right-hand side. A Memristor is a 2-terminal device, unlike a transistor, which is 3-terminal. So it's already a great simplification. It is a 2-terminal device whose resistance can be tuned to some desired value by applying a voltage signal, and which remembers its resistance after the voltage source is disconnected. In other words, it remembers its past. You don't have to use a battery to keep what do you remember? It remembers its past. That's why it's called a memristor. There are some significant virtues that make memristors very important. It's an enabling technology, in other words. Memory is for free. Like I say, there's no battery. No battery is needed to retain its memory. Number two is very high speed. We're talking about nanoseconds. Number three, very low power. Nanowatts is what is involved. Very small, nanometers. We're talking about really tiny devices. Great data retention. You can keep the memory for a long time. Great endurance. And most important, without this, it would not be a post-war era device. It is compatible or compatibility with CMOS technology. You don't just throw away what we have after billions and billions and trillions of dollars spent. So the good news is the memristor is compatible. It's an add-on that makes it more powerful. So memristor, the first thing to remember, is different from a transistor. The transistor that used in CMOS technology basically is a switch. Memristor is not a switch. Memristor is a continuum. In other words, it's not binary. It's all the numbers in between 0 to infinity is included in a memristor. One of the key aspects of deep learning that make all kinds of advances in AI technology today is based on what's called the dot product, which is the vector or matrix product of two numbers, presently two digital numbers. But that is the Achilles heel today, because it takes too much time. It's been estimated in deep learning, it takes about 75 to 85% of computation are all involved just doing one thing, to add the product of two numbers. And that is called the dot product. Most of the time is wasted doing that. Most of the energy wasted, the money paid for doing this job is just adding the product of two numbers. Now, there is now technology developed that will do that much faster, and that is using memristors. What you seen here in this slide is one of the early technology made by Hewlett-Packard, and just to show you that it's already make a difference. And there are already commercial products. This was made a product from Fujitsu about 3 years ago already. It's ReRAM. It's a resistive. It's a code name for resistive random access memory. It's a commercial product introduced already 2 years ago, and in fact, most of the important products nowadays that you don't even pay attention to are already incorporating memristors that they don't even tell you, but it is in there. For example, smartwatch, anything that's small, that looks incredibly small and powerful, has got to have memristors in there. Smartwatch, for example, on the left, or the famous Apple Watch, for example, has memristors in there. Smart glass, hearing aids, the smart hearing, and all kinds of new products. So Nature Electronics has asked me to write an article to give a short one-page description of how I predicted the memristor. And those of you who are interested, you can read it in Nature Electronics on May 14, 2018. It's only one page, so it'll be a simple read. Or an extension of that is in the IEEE Micro of the IEEE Computer Society, and you can read it on the volume 38, issue 5, September 28, 2018. This is an expansion of the one-page article that I just show you in Nature Electronics. Okay. So today I'm just going to briefly give you a quick introduction on how I got to invent the Memristor. Shortly after the invention of the transistor, 75 years ago, there was a rush to invent new devices that hopefully would complement the transistor. As a result of that, there is what I call the perfect storm in nonlinear circuit theory, and I'll briefly describe what it is. One of the first devices that was invented is by Dr. Leo Esaki from IBM, who got the Nobel Prize for this invention, and that was in the Nobel Prize was 1973. But the invention is in 1958. So only a few years after the invention of transistor, and that was the motivation to invent more devices to hopefully bolster the transistor. And thereafter, many more devices, all two terminal I can see, and all have a strange IV curve on the right-hand side. I'm just flashing many of them here, and they're all nonlinear. There are at least 30 of them here. So the problem with so many devices here is that nobody knows what to do with them and how to use them. The pre-1970 definition of the three basic circuit elements that all of you know, called capacitor, resistor, and inductors, give unrealistic or even incorrect circuit solutions when the elements are time varying or nonlinear, as you just saw. The whole table of those, they're all nonlinear. And if you use the theory that was available then, that was taught in schools, in electrical engineering, often you get wrong answers. That was the crisis. And the crisis is the own definition of the three elements. First, the capacitor in 1745 by von Kleist, then by Ohm in 1827, and then by Faraday for the inductor, who invented inductor in 1831. We are going to come back to Faraday, by the way. I just remind you now, okay? And these are the three definitions you now learn in high school, the three circuit elements. They're all linear. They are the one that caused the problem because they gave you the wrong answer. So to show you that the problem, how serious the problem is, even in 1963, another Nobel Prize winner, Richard Feynman, that I'm sure all of you met in physics, a legend in physics, but he himself, even in 1963, in a classic book that he wrote, he didn't even know what a capacitor is. In his classic textbook, volume 2, 1963, Feynman, this is the book called Feynman series in physics, that almost everyone in the 60s used as a textbook. On this particular page, Feynman says the coefficient of proportionality, called the capacity. When you talk about a coefficient, Feynman was referring to C, for example. You know, C, R, L are the three magic numbers that every one of you learn in high school. When you learn about circuit theory, those are the three magic numbers. But Feynman learned that, but he didn't even know what really come from. And so he said the coefficient of proportionality, in this case, the capacitance, is called capacity. And such a system of two conductors is called a condenser. Even Feynman at that time didn't even know that there's a name called capacitor and there's a name called capacitance. And that was the state of the art. That was the problem. So to recover from the perfect storm, capacitor, resistor, inductor must be redefined via an axiomatic approach. In other words, the problem is we had learned from a circuit theory that had become obsolete. We have to introduce a theory that will never become obsolete. And that theory has to be an axiomatic approach. So all resources derived from axiomatic approach must be time, and by definition, they are timeless. In the sense, it will never be obsolete. So it's worthwhile for you to learn it because it will never become obsolete. So very quickly, I will just briefly introduce what this timeless definition is. All of you have learned 4 basic circuit variables: the voltage on the upper left, current in the upper right, charge on the lower left, and flux on the lower right. And these are things you learn even in high school, in fact. And the definition of flux, of charge on the lower left, is the integral of current. Of course, all of you learned in high school, day 1 in high school, in fact. And you learn flux is the integral of voltage. So these are 4 standard variables you all learn. There's nothing new about it. It's a definition. So it's not a concept. It's just a name. Okay. Now the axiomatic definition of the form for the circuit element is if the 2 terminals, if you have a 2-terminal device, and you found that the voltage and the current always obey a particular curve in the voltage current plane, that device is called a resistor with a symbol below it. So that upper red line connects a resistor and defines what a resistor is. That's what it should be. And that is immortal, never become obsolete. If a device didn't have that property, but it obeys instead a relationship, a curve between current and flux, and that device, if it exists, is called an inductor. Of course, in the special case, if that relation is a straight line through the origin, then it relationship is just the usual inductance. If a 2-terminal device didn't have either the 2 correct behavior, it may obey a relationship between the voltage and the charge. And usually that would be a curve, and that would be called a nonlinear capacitor on the left. And of course, if it's a straight line, it reduces to the classical capacitance definition. So this is the correct definition, the timeless axiomatic definition that should be taught to high school students today of a resistor, inductor, capacitor. And especially when they are linear, that would be the correct definition. But if not linear or time invariant, you will have to use this definition indicated here. But if you take this definition that I used, you will see immediately there is something missing. What about the lower connection, the lower relationship? It looks strange that you have a theory that has something missing. So it's a missing link. So I say something got to be there. Some unknown, yet unknown element got to be there. And of course, I was motivated. And that missing element, by the way, is going to be called a memristor. And that relationship would be a curve in the flux versus charge plane. Okay. So Memristor, I published a paper in 1971, 51 years ago. I called it the Memristor, and it doesn't exist then. So I call it the missing circuit element. But in that paper, I actually built one. It's clumsy, but I show as in proof of principle that it works. But is impractical. It occupies about the size of a shoe's bag with two wires coming out, and indeed it will obey, it will have the property of memristor, but it has been forgotten. And what the reason I have a strong belief that it ought to work is, I knew about Mendeleev, who came up with the periodic table in 1869, and this is in Russian, but you can see that there he listed all those elements, chemical elements that are already known then. And on this page, you can see that there are three red boxes that there were non-element that would fit the description then. So Mendeleev would just give the number there that it ought to be, and with a question mark, what it is, but he said it should exist. That's called an axiomatic approach. You believe your theory is, if your theory is correct, it ought to be there. And indeed, we now know that that the upper one is just gallium, the lower left is scandium, and the lower right is germanium. So that was the background that led me to say that the missing link got to be found, and it's the missing circuit element called memristor. So in 2008, Stan Williams, Dr. Stan Williams, the picture on the upper left, the director of the famous quantum mechanical electronics lab in Hewlett-Packard, published a major classic paper called The Missing Memristor Found. And it was published in Nature and highlighted on the cover, the memristor missing element found. That has kicked off the area, and that has become widespread today. And that was a device made of titanium dioxide. And if you look for the characteristic in the VI plane, it is a curve, all right, but it is not a single value curve. It is a curve that has loops that go through the origin. And in fact, you will see today that all memories have to have curves that is not a simple curve, and it always has to go through the origin. So this is already published in when Hewlett-Packard made the announcement on the same day as when the Nature paper was published. It's already an array, and each of the white dot there is a memristor. That the first array of memristor, and they were already very small. As a contrast, this is a virus. This is the smallest virus, 25 nanometer at that time. In 2008, that is the smallest virus. It's already larger than the memristor made at HP, and it has a cell density already of 100. A cell density of 100 gigabits per square centimeter. And since then, there are advances, great advances. For example, in 2013, there's already an 2013, Professor Schaaf from the University of Massachusetts produces an 8 nanometer memristor, and this is the VI curve. You can see it's a loop, and it always goes through the origin. And in year 2015, as you can see here, a group from Northwestern University produced memristor that's only two-dimensional. It's just like a sheet of paper. That was a big advance. And that area has also blossoming up today. Most recently, in 2 years ago, 2019, Nature Technology announced in 2019. There a crossbar memory. This is called a crossbar architecture, and this Memristor there has 2 nanometer size. So we are getting very small already 2 years ago. By the way, just for those of you electrical engineers who are not so familiar with how small is 1 nanometer, let me tell you that the first person who had an idea of that was Einstein. Einstein's PhD thesis was one of the problems asked by his supervisor is to estimate the size of a sugar molecule. I remember Einstein was asked in his PhD thesis to solve the problem of how big is the sugar molecule. And his solution, that made his thesis, one of the problems he solved is it is 1 nanometer. So we are talking about Memristor today that has a size of 2 sugar molecules. That is that small, and it can be now even smaller. And if there already exists, in fact, a 1 molecule Memristor, but that is more of a theoretical interest because it doesn't seem to be possible to build in bulk. So I will now, instead of give you a complicated theory today, we would this is the most practical definition. For those of you who don't intend to be specialists, you want people ask you, what is a Memristor? It is very simple. If you plot, if we take a 2-terminal of any device, and you put in a sine wave voltage and measure the current, and plot the relationship in the V voltage current plane, if you get a loci in that plane that is always go through the origin, such as the one on the bottom right, it is called Memristor. It has to go through the origin. That's the point. So it's easy to remember what a Memristor is. And that is, if it's pinch, it is a Memristor. In particular, to be more precise, if it's pinch at the origin, it is a Memristor. There's nothing simpler to remember than that. That's what a Memristor is. If it's pinch, it is a Memristor. Now, first important take-home lesson today, all non-volatile memories based on resistance switching are in fact Memristor. Most people didn't realize that there are already many devices in the market. There are memories non-volatile based on resistance switchings, and they are all Memristor. For example, some of them are RE-ROMs, MROMs, CB-ROMs, phase change memory, ferroelectric memories, atomic switch, and there are even more. They are all Memristors in the sense that they are all pinch at the origin. And all of this Memristor, the good news is, unlike the transistor that are made from silicon, or mostly are made from silicon economically, Memristor can be built from all kinds of material. For example, RE-ROM Memristor are made from metal oxides, many kinds of metal oxides, like titanium dioxide, tantalum dioxide, etc. Or polymeric Memristors made from conducting polymers, ferroelectric Memristors from ferroelectric films, manganite Memristor from perovskite manganite, spintronic Memristor from spin transfer torque, magnetic layers, etc. So that's the good news. In fact, if you look at the periodic table, almost half of the elements have been used to make Memristors. And almost everything switches. That's a cliche now here. So Memristor is a very generic device in the sense that it's very easy to make. There are many materials. Almost half of the periodic table you can make Memristors out of. The question is, what's the cheapest one that is available. So now we can ask the question, all of you have been using the USB flash. You say, oh, that chip is widely available, so why not use them? Well, there are a number of reasons. First of all, it cannot be scaled below 20 nanometers. It has very poor retention time. Often it fails after switching between 10,000 and 100,000 times. It has low speed, relatively low speed, and it consumes a lot of energy. So that's the reason that it's not a permanent memory, in other words. Flash is short-term memory. Flash memories are not permanent. They lose about 20% of information per decade. So you never store family pictures, especially that of your girlfriend, on flash memory sticks, for example. Non-volatile nano memristors will eventually replace the following conventional computer memories. Flash memories, DRAM, hard drive, they're all going to be replaced by memories, memristor memories. Non-volatile memories are estimated to be, even in 2020, a $400 billion industry, and much more today. And you can make memristor in three-dimensional cubes. In fact, it's been estimated that the entire Library of Congress that contains 21 million, more than 21 million books with 10 terabytes of memory can be stored in a single cube made of memristors. And ever since the HP Nature paper, memristor, the number of papers published in memristor starts in 1971 with almost nothing and remains almost nothing, and it explodes exponentially after 2008. You can see this is about 4 years ago, and it continues exponentially. So you can see that the memristor is the coming things to study and to exploit. The quest for building nanoscale solid-state non-volatile memories dates back, in fact, to 1939. It's not a recent event. It's just that it has never taken off because people saw them, made them, didn't know what they are, and therefore they know their potential. For example, as early as 1939, was covered up there. As early as 1939, a paper was already published. In this is a picture from that paper, 1939. They also published in this paper a picture of the IV curve, and it's pinched. With my definition today, it's a memristor. But Mr. Brice and Hickling didn't know. And in fact, were somewhat ashamed. They were trying their best to make them disappear. The loop disappeared. It didn't disappear. And it was dropped. In 1930, the date is all covered up. It's 1938, I believe, and by Pravin and Pratini. And it's an embarrassing curve that also, is embarrassing. In fact, published a one-page letter to IEEE proceeding, IEEE, I believe. And we now know today that's a memristor. Why? Because it's pinched. The author, as I said, was apologetic. They couldn't make those loops disappear. Another, in 1935, by Chopra. And the picture is not so clear, but there is a curve that connects these two loops here to the origin. It's pinched. Therefore, it is a memristor, but it was dropped because the authors couldn't get rid of the loops, didn't know what it is. Since the Esaki diode, you can see that there are all kinds of curves, they're all pinched. And none of them knew it was the memristors because they didn't know the theory. They didn't have my paper, 1971 paper. They have to wait for my paper. We now know that if you go back to the early days of the first radio is made out of gallium, a crystal. And that gallium was traced recently by one researcher from India, in fact, and it was found to be pinch. It is a memristor. You can say the first radio was made of memristor, in fact. So this is a typical example of a textbook example so that people will understand what the memristor is. So this is the typical textbook example that has an equation. So you can actually plot it. You can see it's pinch, why it's pinch. So, and in fact, for practical purposes, people this wasted a lot of space. So people like to just use the semi-log plot so that the negative part becomes the positive part. And when you do that, this becomes like that. And it looks like what this picture becomes this picture. So often, until my people would not know what a memristor looked like, and they just see curve like this. You know, a curve that I call now a gold wing hysteresis loop. It's pinch. If you see this in a semi-log, this is now log plate or semi-log plot. It is the same as that in this regular coordinate system, and it's pinch. They are memristors. So that is called gold because it looks like gold wing, and like the Mercedes-Benz, it's open like that. Those are the gold wing. And I'll show you now. There are all kinds of ways to make memristor, all kinds of material, including silkworm, a paper published not too long ago. Made of silkworm fibroin protein, and it will show you how to do this. And I show you this is the regular pinch hysteresis loop, but the semi-log plot you can see it's a gold wing plot. And this is you can even get egg white. This is another paper published, in fact, not too long ago. Unfortunately, this slide is cut off in my plot here. If you get the albumin, which is the white part of that plane, you can make a memristor out of that, and you can see it is a gold wing curve. It is a memristor. So, but the most significant paper that has kicked off the area is this paper published in 2000, year 2000.
Professor Chua, Professor Leon?
Yes.
Yeah, the slides, I think they are not moving right now.
You can see the year. Okay, I'm sorry. In my place, it was black up, so I thought you didn't see it. Thank you. Okay, so.
Yeah, can you please put it in the slideshow mode? Yeah.
Okay, so I want to show you now. Let me show you first, gentlemen. This is Johannes Bertnors, received the Nobel Prize. I told you there were many Nobel Prize person today. He's one of them. 1987 Nobel Prize in Physics for discovering high temperature superconductors. He was a co-author of this paper shown here, and it's a pinch hysteresis loop. Of course, Bertnors, he's the second author here. He didn't know it is memristor, but he knew the property, and he published his paper. And even before him, there were many other papers of this kind of curves. People don't pay attention, but because Bertnors' name was there, a Nobel Prize winner, a famous Nobel Prize winner, people pay attention, and they begin to look at some of his statements. One of them statements, he says, a negative voltage pulse of 2 millisecond switches the system into the low impedance state, and after applying a positive voltage pulse of 2 milliseconds, the information written to the device is erased and the high impedance that is restored. So it's showing that you can switch from the high impedance to the low impedance. It's switch, in other words, a binary switch, using pulses, voltage pulses. And that's important because he showed that you can use pulses to switch a two-terminal device, something that's already reported, but people don't pay attention. And he also have a footnote to say that, moreover, in this same paper by Bednos, on this paper, he said, and I reproduce here, faster switching speed, that is shorter write and erase process as used here in this paper are also possible, but require higher amplitude. In other words, Bednos says you can switch by using pulses, but you can even make switching faster by making the pulses larger. In other words, what he is saying is that it's the area that counts. He didn't know why. He just reported it. You will know why today. In fact, at the very end of my talk, you will see why. So, also in other paper after Bednos, it's been reported that although such a resistance, I just copy one of the sentence, although such a resistance transition phenomena has been found for many years, including the Bednos paper, the correlated physical mechanism is still not well understood. Today, the electric pulse, when the pulse we're talking about a square pulse for simplicity, induced resistance switching or EPIR effect is the most generally accepted mechanism. So the secret, however, behind this square pulse switching is still a secret. It will not be a secret anymore after today. But no one knows how it works. You will know how it works today. So since that time, since early time, 80 years of confused and misunderstood non-volatile memory devices had hindered progress because people didn't know what a Memristor is. And there have been many enigma, paradoxes of phenomena that is clearly true, but nobody knew why. And I categorized them into 5 enigmas. And finally, I was invited to give a publication to explain why. And these were published in August of 2018, few years ago. And the title is 5 Non-Volatile Memristor Enigmas Solved. Those of you who want, or those of you really interested on how to explain all of this unsolved problem, read this paper, August 2018, in Applied Physics A. And there are missing opportunities. In fact, people have seen that. My paper on Memristor, the missing Memristor, was published in 1971. In the same year, you can see 1971, a group of Japanese published a paper, and it says polarized memory in CDSC point contact diodes. He said a device, the title is a device dubbed letter 8 memory. Letter 8, you see, polarized letter 8. This is the letter 8. They published this curve. It spins. It's a Memristor. Had they known my definition today, they would, in fact, it's published same year as my paper. I didn't know about this paper. I would have just identified that there exists a Memristor in 1971. And the area would have taken off. So that was one missed opportunity. The second missed opportunity is from a Nobel Prize winner. All of you, or most of you know Brian Josephson. Picture there. He discovered that superconducting Josephson tunneling junction and got the Nobel Prize in 1973. He is famous for producing this junction, Josephson junction circuit model shown here, and he was able, from quantum mechanical argument, that's what he got the Nobel Prize for. It's non-trivial discovery using strictly quantum mechanical principle. No one before him could dream that this is possible. That's where the Nobel Prize came from. But Nobel Prize, or no Nobel Prize, it was not complete in the sense that he didn't know. It was incomplete in the sense that the equivalent circuit published by Josephson was that his device is two-terminal, and the motor consists of capacitor, resistor, and the device that we know today is an inductor. He didn't know it, but he has an equation between the current and the flux. We know today that's an inductor. So it's not strange. And he had an equation. But what is strange is Josephson said there is another element that is fortunately, Josephson says fortunately, is insignificant current. You can neglect it. But to be precise, as the Nobel Prize winner should be, he said it's actually there. And that element obeys an equation like that. And if you plot this equation, it is a curve in the flux versus charge plane. It is a memristor. So already in this paper that Josephson published, he already had a memristor. No one knew. I didn't know. So that was the correct model. That was published in 1976. Those were the two missed opportunities. Okay, so now after the publication, the HP Nature paper in 2008, the areas exploded. So for example, it was almost immediately shown. 2 years later, Lehonen from Finland and others published a paper in 2010 showed that only 2 memristors are needed to generate all 16 Boolean functions. And for example, they also showed that you only need much fewer devices to make a full serial adder. For example, the standard serial CMOS full adder requires 50 transistor. This is the full CMOS adder flip-flop, D flip-flop. You need 50 CMOS transistor. Lehonen showed you only need 10 memristor to do exactly the same thing. And now I want to show you a paper published in 2014 from a group. I was a co-author, but my contribution is insignificant. The main work is by Dr. Liu and his supervisor, Professor Wu from UC Berkeley, who actually, this is called actually this is a catapult, like a medieval catapult. You put a weight here, release the chain, and it will catapult distance away. But Liu and Wu essentially developed a memristor device that will do the same thing. And this is such an advancement because this is an actuator. If you want to build an actuator that will go into our body, our blood vessels, you will need a device like that. And that invention, that publication led Professor Wu from UC Berkeley and then Dr. Wu Liu to receive this presidential early prize with Obama presenting the prize in the White House in 1914. So what is this device? This is the device that is made of niobate dioxide, and it device is, you see, it has a pin hysteresis loop, so it's a memristor. Now I want to show you a video to show you how it actually works. So this is a video that I'm going to show you now, and this is the nano object, and imagine this is a nano stone, okay, and Okay, so you see that I do have. Okay, let me see. What's this? Okay. Yeah, see that was thrown. So that was a demonstration. So let me now move on. Okay, so what this device is it has an immense amount, a great deal of good properties. Let's compare that device with the performance of a Boeing 77. The performance of the micro catapult is compared to the upper part. It has instead of 9 kilowatt per kilogram of the turbojet, it is 39 kilowatt, almost 4 times. And instead of a rotation speed of 10,000 RPM, it's 200,000 RPM. So you can see that this is really powerful device. And now the next slide I want to show you is called an aprecia. It's essentially a sea snail, okay? And what you see there is a Nobel Prize medal on the leg, on the neck. And the reason is Dr. Kandel, who received the Nobel Prize, when he went to Stockholm to receive the prize, this was the picture he flashed. And he said that this aprecia deserves the Nobel Prize. That's Eric Kandel. And what it does is, this is the anatomy of the aprecia. It has an organ called a siphon that's very sensitive. And every time a tiny force, such as something from a brass indicated here, a pulse will be generated that will contract because it senses danger, so it will contract and hide. And Dr. Kandel, in this experiment, uses 15 such shocks or 15 action potential, and he showed only 5 in this paper. 1, 2, 5, 10, and 15. There are 15 of them, and out of these 15 identical input action potential, what Kandel was shocked, and this phenomenon led to his Nobel Prize, by the way, is that first the siphon would immediately lead to the withdrawal of the aprecia's defense organism, and the transducer measures a signal, high speed signal, like large voltage signal, as indicated there. The next signal, that was what the big surprise is. The next signal was smaller, less height. The fifth signal, the fifth shock is even smaller, and the 10th shock even smaller, and by the 15th shock is almost none. And you can easily demonstrate that you can have a simple memristor with a simple curve like that if you apply 15 pulses instead of a signal like on top. So there are 15 signal like that, but instead of action potential, we simplify by just 15 pulses, just like Bernoulli did. Just make pulses, simplify it. You would expect to have 15 identical output, but it didn't happen with that memristor. Correspondingly, 1, 2, 5, 10, and 15, they are getting smaller. So this one memristor did exactly what the aprecia did. That led to Kandel's Nobel Prize. Although he didn't know how it works, we now know it's a memristor working it. So that was the message that I've shown you, that memristor has a strong connection with our brain. It's with neuro computation, the main subject, in fact, of my talk today. And it is in fact the synapse between it is memristor is just like the synapse shown there. Dr. Kandel on the left, and that is the memristor that I showed on the right. Okay. So synapses, we now know, are memristors. That's the one take-home message. The next message is LTP. In 1973, Bliss and Lomo found that a tetanus is just a slang for a short high-frequency pulse train. It's a train of pulses, excitation applied at the hippocampus. So we're now all talking about the brain now. In 1973, Bliss and Lomo found that this phenomena. First, he went to the hippocampus, apply a single pulse there, and found that there is a response, like it's just a pulse, a square pulse. But then, for whatever reason that they didn't explain in that paper, they decided to put, instead of only one pulse, they put in a train of pulses, what they call a tetanus, a slang, and repeated experiments. So now they have a tetanus here. They apply now a tetanus and do repeat experiment, and to their surprise, they found the output is enhanced, it's amplified, and that's called long-term potentiation. That's a big deal today, because that essentially shows how learning came from. We now can show that that's called LTP, long-term potentiation. Depends only on the time integral of the pulse train. That was, remember, the observation, the footnote in Bertnold's paper that I showed you earlier. They have now observed this in the hippocampus, but neither Bertnold nor Bliss and Lomo can understand why. Those are phenomena. Today we tell you it's the memristor doing the work. So this is true with all neurons and synapses. This is a typical neuron, and all those there are many synapses in neurons. In fact, there are more than 100 billion neurons in the human brain. That's a huge number. You know, if earlier I give you a very small number, remember, of a sugar molecule. You know, one nanometer. We can now essentially make 1 nanometer memristor. That was a tiny one. A single sugar. We're now talking about 100 billion neurons. So how big is that? Well, just give you a theory. The Milky Way, turn out, has a little bit more than 100 billion stars. We same order of magnitude. Our brain, your brain, has about the same number of neurons as stars in the Milky Way. And the stars in the Milky Way is actually easy to see. Essentially, every star that you can see with your naked eye is a star in the Milky Way. So all of the stars that you can see with your naked eye are in the Milky Way. And all those stars are the number of neurons in our brain. So now we're just showing the LTP phenomena applies to that as well. And we can now have a memristor, one memristor with that VI curve, simple curve, and it will produce, when it's only a single pulse, apply a single pulse, it would produce an output, a voltage, a single voltage, 5-volt voltage. If you have a 5-volt voltage, it will produce a 2.5 ampere current, just for simplicity. But if you apply the same pulse, but a train of them, suddenly the same input would produce a much bigger. Instead of 2.5 ampere, you can double the output, and it's exactly the same phenomena. So I've just shown you that is what a memristor is. The next phenomena I want to show you is another Nobel Prize phenomena. 1904, Ivan Pavlov received a Nobel Prize for this discovery. He had a dog. You can see a dog there. It's not a very good picture, but this is the original picture. And Pavlov performed an experiment. He had the dog first. He first ring a bell and observe what the dog behave. When he ring the bell, the dog was indifferent. Let me show you. When Pablo rings the bell and observe the dog is indifferent, not very interested. But when Pablo shows the dog a piece of steak, the dog salivates. That's a simple standard observation that you could expect. Then Pablo did the crucial experiment that led to his Nobel Prize. He first showed the dog. Pablo first shows the dog the steak. It salivates. I mean, it showed the bell. It doesn't react, and the steak it salivates. And then now he followed by this experiment where he showed both the steak and followed immediately with the bell. And after that, when Pablo only ring the bell, the dog salivates. The dog has associated the phenomena that when you hear the bell, some goodie is going to appear that he can eat. He begin to salivate. That's called associative memory. So associative memory and learning is defined as the ability to learn and remember the relationship between unrelated experiences or events. In 350 BC, Aristotle had already suggested that learning involves an association of ideas. And a group of scientists from China in Wuhan have performed an experiment and published a paper, and I had visited them, and we deliberate on that, and he put my name as a co-author. I had very little contribution, but this is the paper where I am a contributor and co-author, but had almost no contribution. So this is the experiment. Took a single memristor. This time it's a real memristor that they built in the lab. It is a real memristor. Sorry. This is the real memristor that built in Professor Miao's. The last name is Miao, the professor. You can see below. They built the real memristor there. We can ignore that today and connect 2 voltage sources with 2 resistors. The first voltage source would symbolize a stake. Whenever there's a stake, we would apply this voltage source. When you apply only the bell, you apply the other voltage source. And we performed that, or the Wuhan group of professors then applied this experiment. The top is only the bell, and the second is only the foot, and the third is the response. So you can see that when only the bell is applied, there's no response. When only the foot is applied, there is no response. But when both are applied, there is a response. And when nothing is applied, there is still a response. Exactly what the Pavlov experiment is. So we've just shown you a memristor. A single memristor would reproduce the Pavlov experiment. And now the final experiment is amoeba, which is very interesting. Amoeba, for those of whom probably may not realize, moves. They crawl rather. It's very slow. It's about 1 centimeter per hour at room temperature. And room temperature in this experiment performed by the Japanese scientists is 26 degrees centigrade. So amoeba does not have a brain, but you will see today in the next few slides, it has actually a mind. So this Japanese scientist devised an experiment where a ceiling would have installed cameras, and there are tubes, and there is a cavity where the amoeba will be allowed to crawl one-dimensionally, and these are the temperature. You can blow air in to establish the temperature. So the amoeba start crawling at time 0, and every hour. So, and this is the monitor. So the experiment consists of this experiment here. First, this is this is 26 degree, which normally amoeba would walk. For example, here, 26 degree, it would like to move, but when it goes to about 23 degree, so just 3 degree difference for the amoeba is just like bringing you by helicopter and drop you at the North Pole. That's the same effect for the amoeba. So in 3 degree drop, the amoeba stop moving. So that's an experiment. So the experiment consists of this signals. Every hour, this is 1 hour. Okay, these are the 60 minutes, 1 hour, 2 hour, 3 hour. So in the first 3 hours, where this 26 degree temperature, amoeba moves at its usual slow speed. But at 2 hour, hour 2, suddenly it drops 3 degree, and amoeba drops, stop moving. So you can stop moving, and then and when temperature goes back to 26 degree, slowly amoeba begin to pick up the speed, pick up speed again. So it starts to move again, but then what 1 hour later it drops 1 hour again. 1 hour again. Another drop of 3 degree. Another drop of 3 degree, it stops to move again. And they start to move again. Third hour, it stop again. You see, it stop moving again. And then, but what's interesting is in the 4th hour, where there's no input, the temperature remain constant. On you can see the temperature is the same, but amoeba stop. So you can see the amoeba is smart. Even though the temperature doesn't drop, he predicted that it's going to drop. That's smart, and that is the paper that amoeba can actually learn. So when stimulated by a pattern of periodic environment changes, an amoeba learns and changes its behavior in anticipation of the next stimulus to come. A group of scientists from San Diego devised an experiment with a single memristor and linear RLC circuit and perform an experiment that demonstrate that it will do exactly the same thing. I'm going to run out of time, so I'm going to just tell you that it will do exactly the same thing. So the question is, are amoeba intelligent? The fact that they can do that, you may say, well, that's too trivial. That you don't count that as intelligent. Well, not so. Look, let's look back at the dawn of civilization. What you're looking at now is that in Egypt, go back to the dawn of civilization. Go back to the Nile River. Here is the Nile Delta and the Nile River. Go back to the early human times. Amoeba is actually smarter than early human. Why? Because discerning periodicity, what the amoeba did is they can discern periodicity and realize almost immediately that after 1 hour periodic, you got to do something. You got to stop. The early human didn't know that. Why? Well, discerning a periodicity is not easy, in fact, even for humans. Why? When the ancient Egyptians recognized the regular periodicity, this is a major event in history that's documented. Egyptians recognized the regular periodicity of the flooding of the River Nile, where millions of people died. But the Egyptians soon realized, or well, not so soon, they eventually realized and succeeded in anticipating, like the amoeba, in anticipating the next flood, thus that provided breakthrough would trigger the invention of the calendar, the symbol of the dawn of civilization. Our calendar didn't occur overnight, unlike the amoeba. So they're actually smarter than human in that sense. So we now want to see how our brain evolved. And the next few slides are all going to be on that thing. Look at a squid. And this is the axon, and this is a loligo squid with a big axon. So you can actually see the axon. And experiment had been performed by Hutchinson Huxley, and the experiment led them to receive a Nobel Prize. So here's another Nobel Prize. So you can see all of this get a Nobel Prize. And the Nobel Prize is a circuit. All of this involve a circuit. And this is the circuit that Hutchinson Huxley received in 1976. And the circuit is the regular capacitor, regular resistor, 3 regular batteries, and 2 resistors with an arrowhead that they didn't know what it is, but they called them time-varying resistance. They didn't know anything else. And they got a Nobel Prize for that, in the sense that it is enough to reproduce the action potential that you saw from the snail, the aprecia. That's enough for the Nobel Prize, even though they were wrong. They were not time-varying conductances. They were memristors. I proved that they were memristors. In fact, already in my paper in 1976, after 71, in 1971, I proved that Huxley is wrong. Huxley is wrong. The 2 time-varying resistors that they call time-varying are in fact memristors. And the correct model is this model. The equation that they earned the Nobel Prize remained unchanged. So they deserved the Nobel Prize, but they didn't know they were memristors. And Galvani, let's go back now 200 years. Luigi Galvani asked a very deep question then. What is Galvani? Let's call it all or none enigma. remember what the action potential is. It's either you don't see anything and all of a sudden, boom. It's all or nothing. That's what later people give the name, all or none, or action potential. Well, it all started in January 26, 1781, long time ago. And by accident, serendipitous, in his laboratory at home, Galvani, on that date, fateful date, he connect 240, that was 240 years ago. All or none enigma was conceived. Galvani was astonished. He was astonished to find that. He was astonished to find that the frog leg, here's a frog leg that he had cut off from this experiment, could be induced to contract by using a Leyden jar almost completely discharged so as to be undetected with the most sensitive electroscope. Galvani's all or none enigma says, how could it be that such a tiny electrical force could produce muscle contraction if it were not setting in motion some internal force? He was not able to answer that. But Galvani was well aware of the doctrine of irritability, which is one of the most important conceptual elaboration of the 18th century. According to Galvani, in the framework of doctrine of irritability, external electricity acting as an excitatory stimulus, a trigger that we would say today, for the contraction and not as direct efficient cause of the observed phenomena. How could it be that such tiny electrical force would produce muscle contraction if it were not setting in motion some internal force and triggering some extremely mobile principle existing in nerves, which would then excite the action of the nerve muscular force? Our Galvani observation is correct, but he was attacked. Galvani's lament says, I'm attacked by two very opposite sects, the scientists and the know-nothing. Both laugh at me, calling me the frog's dancing master. But I know that I have discovered one of the greatest forces in nature. Well, it turned out that Huskin Huxley, 200 years later, almost, was able to reproduce finally, after the invention of the oscilloscope, that pulse looked like. It is the action potential. And from that, developed the famous model that led to the Nobel Prize. We now know that the unknown mechanism of the Huskin-Huxley action potential is the edge of chaos. And there are now many textbooks, even today. These are three classic books that are still used today. And they talk about ion channels, and they have this process. These are the process that actually experimentally observed and put in a textbook. And they are all, the textbook, they all use the word excitable. And they're just the modern word that Galvani's time used called irritable. And these are all fancy words. So what does excitable mean? Excitable, actually, the answer is there is presently no definition. That's the interesting thing. And I will tell you an interesting story. A U.S. Supreme Court Justice, Potter Stewart. We are now talking a lot about the Supreme Court today. Well, imagine years back, a very famous Supreme Court Justice, Potter Stewart. He was at a case on pornography, a very important case. And the lawyer tried to challenge Potter Stewart. He said, Your Honor, what is your definition of pornography? Potter Stewart was taken aback. He was not realizing someone who asked him this question. So he started up and said, there is no definition. But he said, I know it when I see it. And of course, that gives away that he must have been a pornographer, addict as himself as well. So excitable, in fact, means edge of chaos. Another deep subject that I would not have time today, but it's related to the last part of my talk. It's related to the local activity principle, a very deep theorem that I developed, an entirely different subject, a new law of thermodynamics that you may consider as an extension of the second law of thermodynamics. In particular, the second law of thermodynamics says that entropy can never decrease. It has always increased. That's why you have no information. You will have no information, no learning. But we have learning everywhere. You have to have entropy that decreases. What did happen? You need local activity. That's the new theory. It's the new, you can call that new law of thermodynamics, where entropy can actually decrease. And the rest of my talk is all about that theory. And it is the edge of chaos. It says that all devices, electronic devices, with two terminals, including, of course, the transistors, it's just two terminals for today. It's either locally active, which is not interesting. This is the second law of thermodynamics. All else is called locally active. And I have a theory for that. And out of a small part of that, the tiny part called edge of chaos, that I have equations also to allow you to calculate the parameters. The important thing is my theory is explicit. It gives you equation so you can calculate and find the numbers where something will happen. Something that will allow you to do the learning. Something that will allow you to find the appreciate why it behaves like that. Okay, so for the remainder, I've already exceeded my time, but I'm going to need another 20 minutes to tell my story. This is in my book called Local Activity Principle, published by Imperial Press, by a physicist, philosophy, Klaus Meinzer and myself. It was all written by Meinzer, but the whole book was based on my work. All the examples are my work. And this is the Haskin-Huxley equation. This is the four equation. This is the four equations that's very messy. This is now the corrected Haskin-Huxley circuit model that is corrected. And you have to use memristors. And the action potentials can now be explained how it evolved from this, how it evolved from zero, from none, from action, or nothing. And it is started from nothing to something, from zero to nothing. And the nothing here is just a point. And this is I'm showing you the solution of the Haskin-Huxley equation. My theory now predicted it will be either nothing, it's a DC zero here, or a huge force. And without going through the detail, I'll show you that as you increase the force, so let me show you again the experiment of this theory. Okay. This is Haskin-Huxley model. The experiment, you apply an input, you apply a pulse, input pulse. When it's zero or nothing, or zero, you have nothing. And when you have a minute, reach a threshold, it's boom, you have an action. That's what it is. And my theory showed that you start with, when it's zero, you have nothing. And then it starts to, however, grow in size. This is now the size. As you grow from 7.5 to this size, and then to 7.8, it gets bigger and bigger and bigger. So as you get bigger, and eventually there's another big oscillation that I don't have time to explain. The two is going to collide. And when the two collide, what happened? Let me remind you, this is a bit like what we are worrying today about the Ukraine and Soviet Union. We're talking about nuclear war, okay? You have Russia, Moscow is going to send a missile, and Ukraine is going to be sending a ballistic missile to collide with it. That's exactly the situation. The collision is the destruction. What we have is the same situation here. When they collide, what is going to happen? In general, it's going to explode. That will be Armageddon. But when you have a similar situation in electron positron, when the positron and electron collide, it disappear, annihilate each other, just like what would happen in Ukraine if such a thing happened. But in neurophysiology, we had made use of that in medicine. When the two collide, what we have is the annihilation led to a gamma ray. A collision between an electron and positron results in annihilation and emission of a gamma ray radiation consisting of two photons with having an energy of 0.5 megavolt energy. And this is the basis of all PET, positron. This is the standard machine you see in all major hospitals. And now even we have a portable PET. They're all based on the collision. That's why I'm showing all this. Well, the question is what happened when two things like that collide? In all of this experiment, it will disappear and collide. But what happened with the neuron? Well, what happened is when it finally, instead of colliding head on, the magic thing about this, it actually reorient itself so that they become identical and so that they become one unit. So they don't collide. The good news is they don't collide and they merge and become nothing. Nothing is destroyed. And so we have the coexistence of these two periodic voltages, and they one stable, the other unstable. This is from the neuron, from the Husky-Huxley equation. When they collide, they don't blow each other up. Oh, sorry. I'm sorry. Just hit the wrong button. Instead of colliding, because if they hit at the wrong angle, it will collide. But in this case, it actually merged. And when it merged, they don't blow each other up. So instead of Armageddon, the apocalypse is actually nothing happened. So this is all is here, all or nothing. So that's an explanation. I have explained what would happen. Okay. And now I'm going to go to the end, the last part of my talk. The voltage-gated ion channels, as I've just shown you earlier, synapses are memristors. We now know voltage-gated ion channels are memristors. Without ion channel memristor, there would be no action potential, and we would all be brain-dead zombies. Without ion channel memristors, our heart would stop beating. Here is an example quickly that you would appreciate, I believe. I hope. This is called a fainting god. You see, these are a kind of god that when they hear some noise, it will just faint. But they don't die. See, fainted, and then after a few seconds, they will recover, just like normal goats. These are called fainting goats. Okay, so let me move on now. So the problem here is that there's a single nucleotide mutation coming from the alaline. From alaline, it mutates to proline. In the chloride ion channel, remember ion channels are memristors. So this is the reason. We talk about memristor, and some memristor, had problem hereditary, and in particular, it changes from alaline to proline, a single ion channel. The chloride, it causes the goat fainting syndrome. So you can use memristor fingerprints to diagnose ion channel diseases. Since ion channels are memristors, healthy and diseased ion channels have different memristor fingerprints and can be diagnosed via automated digital lookup tables. This doesn't exist today, but it is a potential future diagnosis tool. And channelopathies diseases include epilepsy, myotonia, migraine, diabetes, and others. Actions are made of memristors. Brains are made of memristors. Memristors are the right stuff for make brain-like computers. And now I want to show you two videos. First of all, using memristors, it generates the action potential. This is a memristor, the Hutchinson-Huxley memristor, using Hutchinson-Huxley model using memristors to generate action potential. The next one, I'm going to put that in 3 dimensions. Like when you have a heart and its node is the Hutchinson-Huxley model with memristors, the sodium and potassium memristor, and I'm going to show you a video. So this is not the cue. Imagine that this is a segment of your brain or like in the heart. Every node is a neuron. And now let's look at this or a cell in the heart. And that is the models. And now we put them in using the Hutchinson-Huxley equation with the memristor as the model. I want to show you now. Imagine now this is a small part of your heart. What you're seeing here is like a torus, but it is a moving scroll. That is the thing that happened if it occurred in the heart, and it's called ventricular fibrillation. And if you don't act within a few minutes, you will die. And it is caused by memristors. That's the bad news. But I want to finish my talk today to show you there are many more memristors. This is a Venus flytrap. Down up and top, you can see if you take 2 wires out of Venus flytrap on the bottom left here, put 2 wires in, and you measure it, and you see it has a pinch series through. So Venus flytrap actually is a memristor. And when the insect would touch it, the two clamp-like lips would climb up and catch it and secrete hydrochloric, some acid, strong acid, to digest it. That's what it is. But it is a memristor. And I'll show you now experiment. This is an experiment. Just a tiny piece of string, a white thread. Let me repeat the experiment for you. Just a tiny piece of it would do that. So why is it important? Well, because it is a memristor, number one, and it attracted no other than another Nobel Prize winner. Erwin Neher, the 1991 Nobel Prize in Physiology, he was the one who discovered ion channels, but enough to be a Nobel Prize winner. But he went on to look at many other subjects. One of them, he was able to publish a paper very recently, 2016. A paper published that shows that plants, he showed that two impulses trigger the trap to close. In other words, he explained how the Venus flytrap works. He showed they can count two impulses in this paper by Neher and co-author. Two impulses trigger the trap to close, but only after the fifth impulse did the Venus flytrap begin to synthesize the digestive enzyme called hydrolase and increase their production of a sodium transporter, which is used to absorb nutrients. Various flytraps may record the touches of potential prey to identify insects that are worth digesting. So plants are smart, they can count as well. And it is the reason I show this is not because you got a Nobel Prize winners work. It's because it uses a memristor that works on the edge of chaos domain. That's really the main result of this paper. You better study about the edge of chaos and local activity. It's going to be a great future for you. And there's a device that will do it for you. It is the memristor. So now, even the apple, it put it to wire, it has a pinch hysteresis loop. It is a memristor. Take a sun-salted flower, put in a couple of wires on the left, and you perform the measurement. It has a pinch hysteresis loop. It is a memristor. Finally, I want to show you the main result I would call of my work today. Well, not quite the main result, but I think in fact, I think you would like to know this. Let's go back to the early 1800s. We go back to London. Even at that time, London is a very rich society already. You have the Tower of London Bridge, and you will see the lamppost, and the lamppost is burning at fire. You know, the lamppost is burning gas, and the socialite, the ladies of that time, had not much time. They like to stroll around the River Thames, and so they begin to be aggressive and pose the question to the scientists of the day, say, why don't you use electricity so that to light the lamppost so that we don't smell the fumes? And Sir Humphrey Davy rose to the challenge. He published a paper in 1801 showed that it is possible by putting two electrodes, and if you can connect them with a high enough voltage, high enough means 1,000 volts, so that you can a spark, not only a spark, because a spark would not give you light. you need to have a spark that's continuous, a continuous spike. Then you will have light. He told the ladies, give me time, I will produce you light. And sure enough, in 1800, luckily, Alessandra Volta, where we name Volt come from Volta, invented the voltage pile on the right-hand side. Consists of piles of cylindrical piers. And if you pile them up, you just get higher and higher voltage. So all Humphrey Davy need to do is to put enough of them, and you can get 1,000 volt out of that. That's what he did. By the way, because of that, Sir Humphrey Davy was knighted, and that's why he says sir. But two things interesting happened. First, you see here on the bottom left, a picture of Napoleon on the left side and Volta on the right side, demonstrating in 1801 the voltage pile to him. Napoleon was so impressed. Napoleon is not only a great general, he is actually very keen on science. So he was so impressed, he conferred in this picture to Napoleon a count. He became a count in 1801. You can see this is a court painting. In 1801, that Napoleon declared him a count. But let me show you that it is possible for Davy to produce by using 1,000 volt battery based on this voltage pile. And this is the experiment that I encouraged just a few years ago in London to Professor Hu at the University of London to reproduce that experiment. So this is the experiment with 2 electrodes and put in a high voltage with modern technology. And I want to show you now. He pinches to raise his loop. So it is a Memristor. And now this is the experiment. This is the experiment that led to the Nobel, that led to the continuous spark. You see the sparking now coming, and that was a paper you just saw earlier, published in 1801. This experiment was repeated, and it was shown to be a Memristor. So the reason I'm showing all this is because it's all Memristor. Now, I want to show you Napoleon, in addition to being a general, appreciates science. So when he heard about this invention by Sir Humphrey Davy, he decided in 2000 in 1808, when England was at war, in 1808, when France was at war with England, Napoleon has decided to award Davy the Prix-Napoleon Institute. So you can see that he is a real keen of science. But they're at war at that time. To give this award, Humphrey has to come to Paris to claim the prize. So what Napoleon did, because the harbor was mine, and so Napoleon picked a member of the embassy, French embassy in London in the olden days, and asked him to go to sneak into London and to contact Davy and to bring him a whole bunch of gold bars, gold coins, because franc is not useful in London. And he tell him, invite Sir Humphrey Davy and also his wife to come to London. And moreover, give him this money so that he can ask him to hire somebody, hire an assistant, hire an assistant to carry Sir Humphrey's baggage, as well as his wife's baggage, so that he will have a comfortable trip to come to Paris. He did all that, and it is a very interesting story. Sir Humphrey Davy brought his wife with his assistant, and through some secret passages, sailed to Paris, met Napoleon, claimed the prize, returned safely to London. But why am I telling you this? Who is that gentleman, that assistant that carried the luggage? That assistant turned out to be Faraday, who 8 years later, or 32 years later, invented the inductor. So we now have 4 circuit elements, including this Memristor, who was invented, to be fair, in 1801 by Sir Humphrey Davy. These are historical characters. Memristor now, in fact, is the second device invented. But you'll be surprised, that was not the earliest Memristor. Memristor is about 500 million years old. Why is that? Because a paper published in Science Daily in 2007, published, there was a fossil record of jellyfish. That's a picture of jellyfish. And we knew that jellyfish, and that was a fossil record that was Jurassic era. And that was at least 500 million years old. And jellyfish has ion channels. Ion channels are memristors. We can say memristor is at least 500 million years old. So now I will close my talk with the most important talk, I believe, of today, because you can make your own memristor now. The memristor example that all of you seen are not available. You can't go to a store and say you want to buy a memristor. And the memristor you have seen are all laboratory memristors. Those 2 nanometer memristor. These are extremely expensive. Take millions of dollars to make one. I will show you how to make one now today, very cheaply, on the chip. So the question is, what is the simplest 2-terminal device that can exhibit the edge of chaos domain? Because this is what you need to get all the intelligence. That's what you need. The answer turned out, I can prove, is that you need the device that get edge of chaos. And the simplest device is the memristor. So memristor is very special. It is the simplest device that gives us intelligence. And this is my device, is that it is the simplest, cheapest device that you can build yourself. This is the equation, very simple. And my assistant, my colleague, Professor Wang Yi, professor in university in Hangzhou, China, a famous university, Hangzhou University, with Professor Pepe Jin. We published a paper with me in last December, and we now have another paper that shows this schematic circuit. This schematic circuit is made up of 5 op-amps and 2 multipliers and 15 resistors. You can build this circuit for less than $10. You can do that. You can build a memristor because we build them, and that is the circuit board to prove that we build it, and we measure the VI curve. The VI curve is the one on the bottom left corner, and so it's a little strange curve, but it's a pinch hysteresis loop, and it looks like a corsage. That's why it's called a Chua corsage memristor, because I invented it. I invented it 7 years ago. Published it. I published it 7 years ago, and it has since become an exciting device. I didn't realize it is so simple to build. It was built and designed by Pei Peijin and Professor Wang. So I will now use this device. This is to prove that it works. This is the oscilloscope picture of the pinch hysteresis loop. Show it works. And I'll show you the board. And you can build it for less than $10. And now the paper coming out soon is called Pullman's Memristor. $10, a Pullman can afford it. That's why the title paper, not yet published, called Pullman's Memristor, workhorse's Memristor. This is the circuit. If you add an inductor, 4.7 millihenry inductor to a 220 picofarad capacitor to my memristor, and you connect different voltages, you will see that it will reproduce all the phenomena I just reported. This is the last part, 5 minutes. So this is the circuit. And that memristor, this is called the LC because the inductor capacitor augmented memristor, the Chua circuit Corsa memristor. And that memristor is replaced by this circuit that you can build for $10, less than $10. This is now the circuit with the inductor, the 4.7 millihenry inductor, and the 220 picofarad capacitor embedded. This circuit can be built for maybe $15 if you pay for the million inductor and the capacitor. Okay, now this is the first all or none firing. If you put in a small enough portion, so like Bert knows, he said he can fire with a voltage process, but it had to be big enough. So when it's so small enough, it didn't reach a threshold like what here. It doesn't fire. See, the green is the pulse input, the red is the output. Okay. By the way, the output is the voltage across the capacitor. The output is the voltage across the memristor. Okay, the output is nothing. So it's none. So it's none, and then but if you increase it according to Bert knows to larger, when it reaches the threshold like that, which in this case is about I believe it's about 3.5 volt. I mean even this is not enough. When it reaches about 3.5 millivolt, it fires. You see, and now after that, if you increase even larger, it still fires and it's still the same. And that's what is characteristic of all or none thing is. It either nothing, and when it fires, it remains the same level. Its height doesn't increase. It remains the same. That's what an action potential is. And if I now blow up one of this, I'm going to magnify one of this. That's a all or none. What's called all or none, but it's called action potential technically. Okay, and the square pulse, the minimum quest pulse that does it is 2.6 volt. Would fire that. Now I'm going to show you more example. Here is an example. It's called an integrator. If you fire it with less than 2.6 volt, like here, it doesn't fire. But it will up here. It will just quit and come back. But if you quickly followed by another one, which just like you enlarge the width, as Bergner say, you have to make it wider. If you don't have enough height and you want fire, you make it wider, as we did. We make this close enough, and it fires. See, so exactly what Bergner suggested, but Bergner didn't know why. We knew why. We have a theory, and now, but what happened is, if you do the same thing again, nothing happened. Okay, you have to. So you have in fact, if you wait long enough and you fire again with two, but you separate it with a distance, it won't fire because the integration didn't begin enough to give you enough amplitude. So that's all explained. But there is also another explanation, another phenomenon that my circuit would reproduce now. All of this, by the way, from that one circuit, the LC augmented Chua Corsat Memristor. That one circuit I just show you, that $15 circuit with the inductor and capacitor. You just change the input. Now you apply the same input, it fires only one, but because it fires already up to this time, this is now 2.6 volt. So it should fire already with one pulse, it fires. But then you put another one, nothing happened. That's a well-known phenomenon called refractory. In our brain, if you fire once and you put the same input like what I did here, it doesn't work. This is the classic biological phenomena, physiological phenomena called refractory. And you have to wait a minimum period. In this case, it's 70 microsecond. You have to wait 70 nanoseconds. We put this same pulse here, nothing happened. You have to wait 70 nanoseconds before it fires again. 70 nanoseconds is the minimum refractory period. But interestingly enough, the next time, you don't have to wait that long. You only wait. You only wait a part. Say instead of 70, maybe only 30. Maybe only 30. In fact, 20 nanoseconds, and it fires. So this is a well-known, maybe not so well-known, but it's now people realize this is reproducible, real experiment in your brain. If you fire, you have to wait long enough. Once it's about 70 microsecond, but the next time it will fire. This is the refractory period, but you don't have to wait as the same amount. You wait much less. In this case, 20 microsecond, and it will fire. The LC Chua Corsat Memristor circuit will do the same thing. Next, if you use a much larger pulse, a single pulse, so far those are periodic pulses, you will have a long period here, and they will produce all identical action potential. This is likely LT, the long-term potentiation. Remember, it's called the tonic, the tonic pulse. That the pulse I showed you earlier. This will generate that input. Now, I will show you now that instead of you can get all bursting. This is the famous phenomenon now being widely studied nowadays, because many diseases actually can be predicted by this observation of such phenomena. First, is called, if you put in a periodic, this input is periodic, and I'm showing you a periodic input here, and the bottom is just an enlargement of one of the output. So for this one, with 0.1 millisecond pulse width is 0.1 millisecond, it will generate a 8.9 peak amplitude bursting. It's called a single spike bursting. And if I amplify this is the action potential, one pulse bursting. Next one, I enlarged the period to 0.25. This is now wider, like what Bernoulli suggested. You get 2%, two bursting. Next, 0.4. Just watch this. I'm going to keep increasingly. 0.4. You get 3 bursts. These are all periodic, and the bottom one is the enlargement. Enlargement of one of this. Okay, so the next one is 0.55. You now get 4 pulses. Next one, 0.7 millisecond. You got 5 pulses. Next one, 0.85. You got 6 pulses. Next one, 1 millisecond, 7 pulses. Next one, 1.50 millisecond. You got 8 pulses. All of this are now reported in the literature in physiology, widely studied. My single circuit, my Pullman's Memristor circuit will do it all. And in fact, you don't even need periodic input. You can have a single input, but just vary the frequencies. This is not periodic anymore, but you just vary the successive. The green is the input. Remember, the green is the input. The next one is bigger, wider, and you can see the pulse 1, 2, 3, 4, 5, 6. All of them are generated. And finally, just use the battery. Just use the battery. What do you get? You got chaos. If you want to know more details of all of this work, look at my book. HP invited me to give a series of 12 lectures in 2015. Most of this lecture, all the slides that I gave there, that I gave today, including many of the slides today, are in that series book. If you are interested, if you're serious about the local activity, if you're serious to want to learn about Age of Chaos, read this book. It is available through World Scientific. I apologize for the extra time. Thank you for your attention.
Thank you very much, Professor Leon. I must appreciate your commitment towards delivering this particular technical lecture. And what initially was planned out came out to be a full tutorial, I can say. We initially planned out a lecture of 90 minutes, but I think we have already passed 2 hours, 30 minutes for that part. I really appreciate on behalf of IEEE EDS Delhi chapter about your sparing your valuable time, and to all the attendees who have been there with us. There are a few questions. Do I have the permission to share my screen to display those questions to you?
I'm ready to answer any question. Be happy to.
I hope my screen is visible to you.
Oh, can I read the question and give the answer?
Yeah, please go ahead.
Okay, the first question. How Professor Leon, well, by the way, Leon is my first name, so it should be how Professor Chua thought of implementing simulation of chaos using electronics in Chua circuit. There are many circuit, almost every papers nowadays in the International Journal of Bifurcation of and Chaos will have papers like that. And also there are books published on Chua circuit as well, entire books on it. So there's no shortage of that. And since you asked this question, that's another Pullman's, I call it a Pullman's chaos circuit. I invented a circuit in order to make something available on the chip. You can build Chua circuit for less than $5. Okay. And so if you want to know what about chaos is, just build yourself a Chua circuit for less than $5. Question 2, how we implement CMOS technology in Memristor. You do not implement CMOS technology precisely because it has reached its limit in view of Moore's law. You need new technology and new material. CMOS technology, in some sense, has reached its end, and it uses silicon. You have only one element. You want to make a memristor, you can pick almost half the elements on the periodic table and you can build them. The question is, which is the simplest? The simplest is not necessarily the cheapest, though. So it still have to wait a few more years for companies to beat each other out. Someone's going to win, and whoever wins will find out what's the cheapest element that will make the cheapest memristor with the smallest size. Third question, the topic of quantum computing has been there for a while. And we hear companies like Google and IBM making things to replace traditional bits and qubits. What is it actually, and how it gonna help? Well, it is not a fairy tale. The technology exists, but it is only for certain important applications, important for national defense. If you want to go to war and win a war, and you have to send messages in secret, you don't want your code to be broken. You need quantum computing. There are only a few applications, and it's not cheap. It is not cheap. It will never be as cheap as the Memristor. But you are willing to pay for it because nothing else could do it. Maybe someday you can make quantum computer on the chip, but it will not be in my generation or your generation. It may never be. Third question. The topic of the fourth question. You told that a memristor can have any value between 0 and 1. When we are talking about in-memory computation, does it mean that it can behave like a qubit? Well, not exactly in that sense of quantum interference, at least from my limited knowledge of interference, the basis of quantum technology. Not in that sense, I don't think so. But they will certainly be used as a continuum. Remember, memristor, the strength of memristor is not analog, it's not digital, it's not 0 and 1. Why waste it? It's got all the numbers in between. Why waste all the other things that you get it for free? People are going to start to use it, watch it, and it's going to be powerful. Question 5. Sir, for such memory devices, we often require the forming process, filament formation, or the low resistance state to be very stable. Could you comment on the stability of the bio memristor, such as the ones realized from egg albumin? Well, again, could you comment on the stability? In fact, that was one of the problems of widespread use of memristor technology, to use it not as just a binary, but as a continuum. And the problem has not been overcome. That's the best of my knowledge. I have to admit that I am not a person in material science. I'm basically a theoretician, perhaps more inclined to use mathematics, because I'm more inclined to do things that I can prove. And when I say I can prove, I mean 100%. To most people working in the device area, if a device or what they call a theorem, or even Moore's law, if it works for say 90% of the time, is good enough. They would even call it a law. That's what I call Moore's law. When I call it a theorem, it's 100%. Okay. And that's the difference. So when I say I have a local activity theorem, it is a theorem. It is 100%. Whereas most of the other things you read in the literature, they are not theorems. Or there are hundreds of papers people call complexity. and there are hundreds of papers, thousands of papers even on complexity. They are philosophical papers. They are jargons. They are not science. So there's a difference. And what's important, if you want to do good work, do work that's timeless. You have to do it right. Science, the Memristor, as I presented today, is science. Okay. Question 6. What are the lacunas still for the Memristor to be commercialized in a large scale? Well, the lacunas is to make it stable so that it can be sold cheap. Well, in fact, it's already cheap when it use it for specialized application, like what you have seen on the Fujitsu chip in many IoT devices. The manufacturers don't even tell you that they have Memristors in there. The smartwatches, they don't tell you for two reasons. It's now Memristors now are in some sense commodities. The second reason is you may have to pay HP or some other company loyalties if you reveal that you have made some devices that are in fact patented. So you don't advertise that you use Memristors, but they are all over. Okay. Number 8, there are various kinds of ions. There are various kinds of ions are released at a synaptic knob to communicate with other dendrites. How a single Memristor can accommodate the behavior of all these ionic activities? Well, since Memristor is dirt cheap, you can just use numerous Memristors, one for each ion. Why not? Number 9. Professor Chua, thank you for your presentation. Do you think there will be a future where the synaptic functions in the brain could be enhanced or even be replaced by Memristor devices in order to enhance memory or other cognitive ability? The answer is 100%. You're going to see them already. You want to implant things in your. First of all, you have seen the catapult, right? It's so powerful. It's 4 times more powerful than any other competitors. Okay, and I mean 4 times more powerful than the scale when you scale up to the 777 Boeing jet. So it's already being used because it is endowed with properties that you do not get with any other device. So all of those functions that needed this property, there is only one road to go, and that's a Memristor, and it's dirt cheap. Why is it cheap? Because there are so many ways to make, so many materials you can pick from, so many ways to make them, and they can be made very small. Like I said, you already have publication in Nature Technology of 2 nanometer, and it's already possible to make 1 nanometer. It's just that it's expensive. One sugar molecule. Think about it. But if you want to work inside the body, you want to navigate inside the blood vessels, the veins. To do something, you want to cure somebody, you need to actuate. You want to open up some blockage, you need an actuator. It got to be small, and it's got to be powerful, like the catapult. So you can see there's a great future in the future. That's what I believe. I think I should also say that it has a lot of cognitive ability. and all learning requires memristors. Again, I apologize. I've already consumed much more of the time. Thank you.
Oh, thank you very much, Professor Chua. And to all the attendees, I must appreciate at your age and taking out so much time. And it's exactly midnight when I'm talking to you right now. So I was saying that so much to learn from your lecture. Be it history, you have turned the pages to 300 years and you've tried to correlate all the possible discoveries which have been made in past with the inventions which have taken place in last 50 to 60 years. So that's that correlation which you have brought up. That is really interesting, intriguing, and a learning for all the young budding scientists who always look up to different aspects of the technology and engineering part. But it's always important to go back to your roots, look at the various events which has happened in the historical aspects of the science and engineering. So on behalf of IEEE EDS Delhi chapter, I would like to thank you once again, and to all the attendees who have been there with us for this inaugural technical lecture series, which we are organizing as part of the 75th anniversary of the transistor invention. Thank you very much, Professor Chua.
My pleasure.
Thank you. Thank you very much.